Hello, everyone. Welcome to today's MLSS lecture. It is my honor to introduce today's speaker, Dr. Biking. Dr. Biking is a staff research scientist at Google Brain. Her research focused on improving interpretability in machine learning by building interpretability methods for already trained model or building inherently interpretable model. She gave a talk at G20 meeting in Argentina in 2019. Her work, TCAV, is amazing. It received UNESCO NetTechFlow Award, was featured by Google I/O 19, and in Brian Christine's book, The Alignment Problem. Dr. King has given keynote at ECNL 2020, tutorials on interpretability at ICNL, University of Toronto, CVPR, and at Lawrence Berkeley National Laboratory. And several years before, when I started to survey interpretable machine learning in order to prepare my machine learning course at National Taiwan University, I went through all the related tutorial I can find online. And Dr. King's tutorial really amazed me and formed my understanding about interpretable machine learning. So when I plan to invite a speaker talking about interpretable machine learning at MLSS 2021, Dr. King is the first candidate coming to my mind. And it is our great pleasure that she accepts the invitation and will talk about interpretable machine learning for us today. Please join me to welcome Dr. Tin. Dr. Tin, now the stage is yours.
Oh, thank you. Thanks for a generous introduction. I am honored to teach at MLSS because myself was a student many years ago at MLSS. It was back then in Tübingen. And I remember meeting many researchers there. Zubin, I met him for the first time there in Tübingen. And I remember thinking he gave an amazing lecture. And I remember thinking, wow, he's just very energized and like clicking his heels and all that. And I was really energized in his lecture. And later, funny story, somebody told me, hey, Zubin was really energized today. And I was like, yeah, this is great. And this person told me Zubin's not always like that. But it happened that he had huge jet lag trying to fly to Tübingen that night, and he had drinking a lot of coffee. And I feel like I'm in a little bit of Zubin's shoes today. I have my coffee. I have a 1-year-old son who refused to sleep last night. But I took a nap and I have coffee. So I'm sure this will all be awesome. So thanks for coming. Let's get started. I'm going to talk about interpretability and why, what, and how to. Before going into why don't we start the lecture with XKCD. This is two friends who are building machine learning system. And if you're here at MLSS, you probably trained a model or two, or maybe you've seen somebody training a model, and see if you resonate what these two folks are about to say. This is your machine learning system? Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Well, you just stir the pile until they start looking right. Is this a problem? Yes. Every day, we're fascinated by AI, what AI can do, and we're excited. We try all sorts of new ideas. We want to build a bigger model. We want to build a model that can code, gather more data. And this is all really great. And thanks to that, we have seen unprecedented advances in AI. AI has definitely let its name known as a powerful tool for many applications. But whenever we encounter something that's powerful, it should make us pause. Because this sounds too good to be true. Are we sure that things are going to the right direction in the long term? Or will we look back in 20 years and have any regrets about what we're doing now? Now, one way to answer this question is to know what we are doing and know what our models know, improving interpretability. And this talk is about that. And so for this reason, this tutorial isn't going to be lists and lists of methods and methods alone, because I think we've invented lots of methods, and that doesn't seem to be our bottleneck. That doesn't seem to be the most important thing right now. So instead, I'm going to talk about more important things. So what are those? We're going to first talk about what is interpretability and why. And then we're going to talk about caution, things that one needs to be careful when using and developing interpretability. And then perhaps one of the most important part, we're going to talk a lot about how to evaluate interpretability methods, to pick when you're developing a new method or to select which method you want to use at practice. Then we're going to finally talk about methods. I'm going to show you 3 types of different methods and examples. So let's dive right in. What is interpretability? Well, in dictionary, it says to explain or to present in understandable terms. In machine learning, we have a few different definitions. Some here, ability to explain or to present in understandable terms to a human. There has been large literature in cognitive science too, one of which says explanations are the currency in which we exchange beliefs. Now, these are all good, but wait, I'm going to write a paper about interpretability. How do I make a working definition? How do I operationalize interpretability? Here's how you do it. You define the desiderata, things, criteria that you need them to be true, and clearly define what that is. And if you're optimizing mathematically, what you're trying to optimize. So for example, define what faithful is and your definition, why your definitions are different from what other people used, so that you can put your work in the context of others and provide, of course, justification. But wait, why are we doing that? Why can't we just have one definition of interpretability? We can all use that all together, right? Not really. And let me ask you a different question. Is there one definition for what we mean by good generative model? Not really. We try a lot of different desiderata and we fail most of the time, as we sometimes succeed, and that's how the field moves forward. And this is all because we can't really use math to define humans. In fact, many problems, even supervised learning, it is rare to have one unified mathematical definition. And that's why proper evaluation is very important. So to claim you have successful interpretability methods, you need to check with the ultimate goal, check with the end task metric, see if it was improved, whether that's about helping doctors diagnose faster or more accurately. And we're going to dig a lot deeper on this in this talk. Then you might say, well, is it possible at all? Are we hopeful? Because I've read these articles that says machines has gone beyond what human can understand. Well, it's okay. The point of the interpretability doesn't mean we have to understand all the bits and bytes of exactly how the model makes decision in a single data point. Sometimes we can't really do this because some models are superhuman performance, maybe some space of the model we just simply can't comprehend. But that's okay, because what we need is knowing how models work enough so that your goals, it's enough for your goals and downstream tasks. Oh, there's a quick question. Thanks for that question. I forgot to mention, please do ask questions interactively. I would love to have the interactive session. It's just better teaching experience. So Roman asks, how to evaluate an overfitted model beyond quantitative performance on the test set? How to understand which part of the model contributed most to overfitting most? I might have some partial answer to this question in the method section where I where I present someone else's great work in one way to do this. But fundamentally, the question you're asking is unsolved question. So let's talk about the methods and see, you can tell for yourself whether this method will fit in your case. And I'll talk a lot about even if this method fits in one case, may not be the right thing to do for another case. Thanks for that question. So interpretability possible at all? It is possible. But what do you mean by enough? What do you mean by knowing enough? Well, let's think about what do we usually mean when we say something the system is, to say, fair enough. Or maybe you have a tool like a hammer and you say, oh, it's good enough. What we really mean is it is good enough for what we are trying to do. It is good enough for our goal. In other words, you're better off having this tool for what you're trying to achieve. And that's exactly the definition of having enough. But what is the goal, right? Ultimate goal that you need to keep in mind as an ultimate thing to improve is your end task metric. What is end task metric? Well, whatever that you want to achieve at the end of the road with this method, either that is about helping doctors to save more patients or helping scientists to discover something new. But in high level, what is generally our goal with this interpretability business? Everyone's goal is different, but I'll share one with you here. Mine is to making tools to help people use machine learning more effectively and responsibly so that our values are respected and human knowledge is reflected when appropriate. Because I think human knowledge, we've accumulated so many centuries. There's some insights or intuition that machines may just simply not able to learn given limited data or given even infinite data. In particular, I care about helping everyone and not just particularly privileged group of people, perhaps us, who happens to learn machine learning and have opportunity to learn what machine learning is. And I'll talk more about a method that can do that later. It is also important to talk about what is not our goal. It is not our goal to understand all the models, of making all models interpretable, because some of the cases, you just don't need interpretability. It's not about understanding every single bit of our model. We just talked about that. It's not about being against developing highly complex models. We have huge complexity already, and that's okay. And it's also, most importantly, not only about gaining user trust or just improving fairness. In fact, here's a paper that was published a couple of years ago that discovered the model uses non-medical confounding patient information to predict hip fracture. And this was discovered to point out that, hey, this model looks amazing, but it's not actually doing what you want it to do. And I often find in my work with product teams at Google, I think helping people to distrust the model is often more important than helping them to trust it. Another important thing to note before moving forward is that interpretability is not a new problem. So why now? Why do we care now? Prevalence, it's everywhere, as you know, and it's used to make many important, potentially life-changing decisions for many. Complexity is another thing. There's layers and layers of models, and I can attest that there exist many in Google. So sure, fine, that's the interpretability of the definition and all that, but when do you need interpretability? You said that you don't need it every time. What do you mean? Well, the reason you need interpretability is because you may have fundamental underspecification in the problem. So what does that mean? Well, it just means that humans can and maybe don't know exactly all the list of things that they want. I'll give you some example. So let's say you're building an autonomous car and you want to build a safe car. Now, do you think that you can list out all the possible scenarios that this car might encounter in its lifetime or maybe forever and write down what the right answer is in each of those scenarios? Probably not, because there's an infinite amount of cases. You can't really specify exactly only once you meet all these criteria, then you are safe. It's a fundamentally underspecified problem. Science, people use machine learning to discover something new. It's something new, so you can't really specify what the new thing is because you don't know it yet. Finally, mismatched objectives. You may try to help your patient with this pill that cures sinus, but patient might have different preferences of what kind of side effects they're willing to have. Like some people really hate headache, maybe some people really don't want to gain weight. And without knowing that clearly, you may actually not obtain the very objective trying to help patients in some cases. And there's a question in the chat, what are the differences between AI and interpretability and transparency? Good question. So there has been lots of different suggestions of what these mean. So definition is in the flux. However, typically I view interpretability as tools to help people understand the model. So actually humans going in and like they can understand. Transparency is best explained using example. I can open source the entire 20 million lines of code for, say, some model that Google uses. It's transparent. You can like look at it. It's an open book. But can you understand it? Can person actually reason about how system works? You can't. So there's a slight difference in the definition that I accepted personally of difference between interpretability and transparency. Let's see. Yeah, Amanda, is there ever a notion of generalized interpretability in broader context, given the highly contextual nature of the term? I think it depends on what you mean by generalizable interpretability. I think there are some notions which we'll cover later about what is the important feature, where the definition of importance changes quite a bit. And some definitions, I think one can argue that it is pretty widely applicable. So let's talk more about that when we get to the method section. Great questions. Thanks all. So here takeaway is that because the interpretability is needed because of the fundamental underspecification of the problem, this is not something that you have more data or you're being more clever can solve. So you might ask, okay, hang on. Sounds like everything is under specification. So when do you not need interpretability? What is not under specification? It is, you don't need interpretability if there's no significant consequences. Indeed, like you just really care about prediction and that is all. And there's no downstream effect that might be significantly impacting people. It's kind of hard to think about example of this because any cases you can argue, but I'm certainly sure in some cases that is indeed what you care. Sufficiently well-studied problem with a lot of empirical evidence that it works, you may not need interpretability. I used to fly pre-pandemic. I am comfortable flying without really understanding how planes work because I've flown many times. I survived. Many other people seem to do it too, although there are some exceptions. So I don't have to understand everything about plane. I'm not comfortable with that. And there are lots of examples like that. People might game the system. If, let's say you have a loan credit score, and if you can find the objective that truly aligns with what you want people to do, then maybe it's not possible to game. However, if there's that mismatch that you can just do this one thing to improve the credit score without really being more credible, then people might be able to game the system. So in those cases, which is quite common, you may not want interpretability. So take away, you don't always need it. But you might say, well, yeah, so that's all good. Sure, I might need it sometimes, but I've heard about this performance trade-off business. And in my domain, I really can't afford performance trade-off because performance is really important. Now I'm here to tell you good news. Famously said by Cynthia Rudin, it is a myth that there's necessarily a trade-off between accuracy and interpretability. In fact, here is the list of a lot of work that's done by myself and many other people in the field that convince you, that supports this claim. And you can think about it this way if this doesn't make sense to you. Interpretability is about building a structure in the model. What is a structure? Well, loss term is a structure. You're building a model to follow this particular path in order to optimize for this metric, this number. Prior is a structure, regularizer is a structure. Now, these things has been done a long time before even deep learning to improve performance. And they didn't think about interpretability back then, but it works, and interpretability could be the same thing. And this is not to say there doesn't exist. It means that doesn't exist inherently. You can improve and achieve both interpretability and performance in a lot of cases. So you might say, okay, so that all sounds fine. There's no trade-off. There may not be a trade-off. So that's cool. So once I get the interpretability, then I'm getting these all other good things too, right? The fairness, accountability, trust, and causality. Hang on there. These things are different they are not the same thing. And perhaps this might be obvious to some people, but oftentimes when we talk about interpretability, people seem to confuse with the other things, fairness and accountability. In fact, interpretability is a tool that could help these to achieve these criteria, to be more fair, to be more accountable. But once you formalize what fairness is, for example, you have a mathematical definition, say equal opportunity, then you don't need interpretability. You just achieve that objective and you're done. So that was what and why of interpretability. And now we're going to look at things that you need to be careful when using or developing interpretability methods. If there's any questions on the first section, feel free to type away. And there will be, by the way, there will be some small quizzes in the way to help you get a little more active and think about later on. So get ready with the chatting room. All right, so let's jump right in. So you might have heard, okay, I've heard that decision trees are cool and that they are always interpretable. Oh, the question. Would you consider giving explanation in terms of natural language as the ideal way of explanation? Thanks, memes. I love cats. Well, I'm a dog person, but I think cats are just funny. I don't think so, actually. And it's an interesting question, and I think the opinion differs quite a bit. The reason that I don't think it's the ideal explanation is because the language itself has its own ambiguity, depending on how you learn English. Like, English is not my first language. So the way that I think about a certain sentence might be pretty different from some other folks reading the same sentence. And because of that ambiguity, and this is pretty well-known fact, that I don't think having an English and natural language form is the ultimate goal. I think it sometimes actually introduces noise. And I'll talk about later one of the methods that the TCAV that Hyungi briefly talked about to see like what kind of format that I think is helpful for a lot of applications. Not the ideal and the best, but probably helpful for a lot of cases. Another question. Difference between explainability and interpretability. This is also another term that gets talked about sometimes. But my answer to these kind of questions are always, you know, it really doesn't matter what you call it. You can call it Mickey Mouse if you want, as long as you clear about what you're trying to do in your paper or in documents that you're writing about. Some people like to distinguish those two, but I personally don't really distinguish those two. But this opinion differs between experts too. So let's go back to talk about the decision trees, because I think this is the part that might be fun and a little bit active. So get ready for your chatting room. So decision trees, you might have heard about this. This is all you need, right? Why are we even having this tutorial? I'm going to, in the next few slides, I'm going to give you a few sample decision trees with increasing complexity. I want you to type the answer that you think is correct for you in the chatting room. And I know there's a little delay between the time now and then your time now. So I will wait a little bit, or maybe I'll just move on and maybe come back to look back later. So here's an example. Pandemic is over. Unfortunately, as far as I'm concerned, it is not over at all, because otherwise I will be in Taipei right now. So it's a no. And there has been COVID-19 variants. Yes, there has been many COVID-19 variants. So in this case, answer would be number 3. So are you ready for next question? Here we go. Give me some time. All right, perhaps you have got an answer, perhaps not, that's okay. Let's find the answer. Pandemic is over, no. We saw no variants, that's not true. Mask up protects you and me. Depends on which political group that you belong to, but I think it's yes, it does protect you and me. And year is greater than 1992, which is 0, and yes, so it's 8. And this is so much fun. So let me see. So I think I think I'm looking at the answers from this. There's a lot of 6s. Very interesting. Let's see. You saw no So maybe the negation was a little confusing. And that's exactly my point of this exercise, because depending on, this is a rule decision tree, right? No one really guarantees that there will be no negation, or there will be unintuitive way of the feature is defined. And look, maybe there is no variant in Taipei actually, but here where I am in Seattle, United States, there are variants. So the answer is typically A. And this is exactly my point. Even this very simple decision tree, it's difficult. It's not easy, and it might take us. It typically takes people a little bit of time. So are you ready for a little more complex one? Here, let's go. And this is fun part. I've done this exercise a couple times, and folks usually, when I show this slide, they like sigh. They're like, oh, man. Taipei's alpha, I see. Yeah. Oh, I see. We have alpha and delta plus too, I believe. There you go. Yeah, I'm seeing the answers. Great. So yeah, let's look at it. So pandemic is over. No. Year greater than 14. Yes. I saw no variants. No. Year is greater than 1990. Yes. Month of January. No. I'm so sick of pandemic. 15. So I don't know about you. The last question depends. If you answer 16, I thought one person answered 16. You should tell us what your tricks are. And maybe you should write a book about it and tell us how you're not seeing it. Yeah, James, I see 16. Good for you. So yeah, the point is that this tree is 5 depth. It's very simple. And it has 23 leaf nodes. Pretty small tree. But still, yet, we're kind of all over the place. But let me ask you another question. Can anybody tell me that what was the overall logic of the system was? How does it typically work? Was there a feature that the model was relying on more than others? It's hard to tell, right? And takeaway here is that decision trees are a good model for some problems, but not always. Here, assumption that I made is that speed is what you care, like doctors diagnosing some patients really fast, or maybe global understanding is your goal. If those are your goal, decision trees may not be your best fit. However, it is a good fit for a lot of other applications. So maybe you say, okay, well, maybe it was because all those trees branching out all over the place. Maybe if you just write down sentence, maybe we can have a list. Maybe that will be a little better idea, something like this. Or maybe not. The thing is, in order to go down to all the way to bottom, let's say code running, then watch TV, you have to ensure everything above it is true. And no one guarantees that whatever you learn rules above it is going to be simple and intuitive. What about rule sets? Maybe we just cluster these rules together, and that's maybe a better idea. Something like this. Or not, making it arbitrarily complex. And if this looks complex, it's actually not that many features. I think it's got like 5 or 6 features and not that many rule sets either. And I'm not saying that decision trees or rule lists or rule sets don't work. These do work. The point here is that there is no one-size-fits-all methods. Just like you cannot have one architecture for all problems in machine learning, same business. I see the question. I'll get to that later. There's a huge difference between the two, perhaps later and when I talk about using causality for interpretability, I'll answer this question. Sorry, the question was, what is the difference between causality and interpretability? In fact, I think it's coming very soon. So another question you may have is, linear classifiers are interpretable, right? Why don't we just fit locally linear functions everywhere and call it done? Not quite. Humans interpret a linear model. That sentence has to have a question mark at the end of the day. So humans can't really interpret models with many features, let alone 10 even gets pretty difficult. And let's even say that you normalize the weights in the linear model and call that the importance of each feature. Famous psychologist Danny Kahneman famously said that humans have this probability distortion, which means that people can people generally don't look at the value of probability uniformly between 0 and 1. They feel lower probability is overweighted, while medium and high probability is underweighted. So we don't reason linearly, even given the simple number between 0 and 1. And so it is not always the answer. It is sometimes the right answer, not always. Here is your answer to your question, Chonghan. Causality should be the one and the only methods for interpretability, right? If you're not doing causality, what are you doing? Well, I am a big fan of causal inference and causal inference framework, and it is a very area of huge importance. There's no doubt about that. And in fact, I have a few papers on using causal inference for interpretability. However, if you've tried to use causal inference for your problem, you may quickly learn that it comes with a lot of assumptions, like no hidden confounders, or you have the right acyclic graph, you have right DAG. And these assumptions form the way that you view the world, what variables affect the other variables. And of course, these start to really matter for high-dimensional real-world applications. And using high dimensions are also found to be pretty challenging currently. Perhaps it will be different in 2 years from now or 1 year from now. I'm really excited about that. So saying something like without causality, explanation is meaningless, I'd rather have some useful, well-validated explanation than nothing at all for high-stake applications. And we'll talk about what we mean by well-validated later in the evaluation section. And I know that assumptions of any machine learning models can be broken. The difference here, I believe, is that there has been many empirical evidence that say IID assumptions were broken, but still perform really well for high-dimensional real-world applications. But in causal inference, I think we need a little more evidence, accumulation of evidence in that. And if you're interested in more, to learn more about causal inference, I randomly encountered this amazing blog by this person I've never met that has a very intuitive and funny tutorial. And I'm happy to share the slides later if you can't really write down this now, but highly recommend it. Let's see. So I have another question I'm going to read. Yu Liang, it seems causal understanding play a crucial role in XAI. The two representative models, agnostic approach, Lyman Xiao and XAI, are simply showing the future contribution for input data. Do you think there's any other approach that could offer causal explanation, like Pearl's causality, such as counterfactual? Yes, and we will cover a few methods like that in the method section. Good question. So great. So we've learned a couple of cautions here. The linear model is not always the answer. Causal inference not always the answer. But you say, okay, so but then once I figure out what kind of method I need for my method, my application, and I got the explanation, that is how models think, right? Not necessarily. Let me tell you a work that we did a couple of years ago, where we show that some explanation fails a simple sanity check. So let's look at some saliency method, which is the typical and very popular post-hoc interpretability method. What is post-hoc interpretability method? You just have a model that is fixed, somebody gave it to you, and your goal is to find the evidence of prediction. In other words, why was this image predicted as Junco bird? And one definition of explanation here is tell me how sensitive the prediction is when we slightly change each input pixel. So if I change input pixel a little bit, but prediction changed a huge amount, that means that pixel was important under this definition. And to put that in the working mechanism, you can use first order derivative. Here, the probability of the prediction, Junco bird, with respect to each and every pixel. And this first order derivative is something that a lot of methods use as the ingredient. And thanks to this kind of beautiful and elegant way of describing importance, there has been an explosion of methods like this, including some of my own work. Here's some few work, popular method 1 and 2 and 3 and 4. And if you look at it, sure, it kind of makes sense. It looks like the method number 1 and 2 is looking at the shape of the bird. Maybe that method, my method is looking at some of the feet. Kind of makes sense. It's predicting a bird, then it's looking at the bird. So, but hold on a second. Let's ask a sanity check question. So the claims that these methods are making is that these pixels are the evidence of prediction. So in other words, there's a function g that takes prediction as an input and outputs explanation. If that's the case, more likely than not that if I put a different input, output is going to be different. Different prediction, explanation is different. Not always, but most of the time. But in extreme case, if I give a random input and do that many times, then really the output should be different. If in fact this function g takes prediction as an input. So we tested this. Here we took a beautifully trained network, classifies images, objects in the images very well, better than humans. And we got many, many images and got many, many saliency maps from them. Then we copied that network and started randomizing the weights from the top in the cascading manner. So, excuse me, we randomized the top 1 layer, we randomized top 2 layers, 3 layers, and until we randomized the whole thing. And when we got the saliency maps, visually those two are indistinguishable. And you might say, well, you know, they are kind of similar, but they're not exactly the same. It looks like the second picture has more dots on the sky. But remember, the goal of interpretability methods is for human consumption. And as a human, I am not sure if I will draw a different conclusion looking at these two pictures. Both of them seems to highlight the belly of the bird, and both of them seems to highlight like the neck or cheek side of the bird. And in fact, 3 out of the 6 pictures that I showed you a while ago are generated from random network. Now, I want you to take a guess. Which 3 things do you think are generated from random network? So chances are that it's from popular method between 1 and 2. Maybe it's one of the my work in 19, 1 and 2. Maybe it's also between one of the 3 and 4. So I want you to guess which one it might be. And I'd be really impressed if anybody can actually do this. Because after all these years, I still can't tell. I know there's a little delay, so I'll tell you the answer, and in the future, you will hear this answer. The answer is popular method 2, my work number 2, and the popular method number 4. These are oh, somebody actually got them right. Yes, all of them. Perhaps might as well. Yeah, so popular method 2, my work from number 2, and popular method 4 are random ones. They're actually quite good answers. How are you doing that? Amazing. But I'm willing to argue that you can't typically do this in under non-superhuman people. So here's some popular methods in each row, and I'm showing you randomized layers from just randomizing logic layer, randomizing top 2 layers, all the way to, in the last column, you're looking at a completely random network. A quick question here, if I missed some details, but are all weights randomized or just the top level layers? Yeah, all the weights I'm showing you actually multiple different randomized networks. So in the second column, I'm showing you just logic layer randomized, which means that the prediction is already random, but the rest of the weights are maintained. And then in the third column, mixed 7C, I randomized both logic and mixed 7C. So, oh, you just answered. There's some delay. Yeah, and the entire column is entirely random. Cool. I'm glad that my past self already answered. So after this discovery, we showed that, yeah, there's some methods don't even change visually at all as we randomize this. Saliency, is it attention? Yes, I might have used it in exchangeably, but attention map or saliency map, these are attribution map, these are some different names for the same thing, pixel-wise, using gradients, importance map. So after that work, that discovery, we thought, that's weird. Can we do something else crazy? So instead of getting saliency maps for a random untrained network, why don't we train a network with random labels? So this network that we're about to train cannot learn meaning of numbers, because we call number 2, this is number 2, this is number 4, and number 5, we said this is number 7, and all over the place uniformly. So it didn't learn anything. And yet, if you look at the second row, it looked like it almost kind of learned the digit 0 in some of the methods. And in fact, the raw gradient, which is a lot of these methods, what a lot of these methods are based on, this is the raw ingredient, seems to be kind of showing the right thing. And this is something that we repeatedly observe, that raw ingredient is actually trying to show the truth. And at least that's what I expected to see. So yeah, that's sort of shocking results of how some of these methods don't pass saliency map. And it doesn't end there. Explanation can be easily attacked. And this might be easy to imagine if you're familiar with adversarial examples. You can optimize for a particular direction in this neural network because it's so high dimensional. You can trick kind of almost anything. And of course, you can trick explanation too. In fact, one of our work on the last picture, we were able to introduce a constant shift that shaped like a cat, because why not, for fun, and so just so that we can call it catastrophic attribution failure. We can actually arbitrarily make this arbitrary constant shift to appear in saliency maps, and we were able to do that. So, and there's a little more to that. Approximated explanation, which often happens in post hoc explanation methods, because these are approximates, it will make some errors, and sometimes it's just plain wrong. And a lot of methods spoke to that very fact, that it is not robust. It is that it is easily breakable. So that is all to say that you have to be always skeptical about the explanation you get. And I wanted to kind of deliver this before I get you all excited about methods, because you always want to have that skeptical mindset when you're looking at explanation methods of any kind, really. And here you might also ask, okay, well, we already know all the learned parameters of the function of the neural network. It's an open book and transparent system. And believe it or not, this has actually been said by a very prominent researcher. I don't think I have to talk a lot about this. Come on. Maybe this is true if you're the one that, and like maybe smartest person in the world, and all day and every day what you do is to stare at neural network, and you just have develop this amazing superhuman sense of reading these weights. But it's not just about you. Machine learning is a powerful tool, and we want the tools to be understandable and usable by a layperson, regardless of their machine learning expert knowledge. So I argue that this is not probably not the goal for a lot of people. And lastly, you might say, I'm a machine learning person. I don't run human experiments. I know that interpretability has to do with humans, but those are for HCI folks, right? Not really. How you present your explanation is as important as the explanation themselves. In other words, best way to ruin great explanation methods is to have poor presentation. But it's even trickier than that. In fact, you don't want to have too good visualization. So here's a few work that shows one that they found in the work on the left. They found that participants were overtrusting the tool because they're excited about the visualization and took them at face value instead of digging them deeper. And another work that pointed out this well-put quote from this paper: illustrated power of visualization is a double-edged sword. An evocative graphic can elicit strong feelings of comprehension, regardless of whether the graphic faithfully represents the phenomenon it is attempting to depict. And that is so true. And so takeaway here is that human factors is tricky. It's not really just about do we really well, do we make it really just so great. You have to still tease out this second human factor, how humans would perceive and how much impact the visualization or presentation itself would make to your users. So it's very tricky, very important. So before I move on, let me just quickly check on the chat. I think I might have missed one question. Did I? What should be the ground truth of an explanation method? Good question. I will get into that in the evaluation section. And if I still didn't answer your question, then please ask again. Another question, could you provide more insights on why such an intuitive way of using gradients to probe the network can fail the sanity check so easily? Is this because the saliency map method or the network itself? It's a great question. To answer it directly, we don't know yet. We don't know why the random network gets us visually indistinguishable results. I will show you later, as actually in this section of evaluation, there's a work that we did as a follow-up to actually test this saliency method with humans to see, we think it's something there, we just don't know what it is, but does it help users to solve the end task, what they're trying to do, no matter what it is? And we have some partial answer to that question later on. Network itself, the gradient itself is just a function, right? It's a mathematical function. I think there's a couple of other issues going here, that the images, humans are trained to process images in a certain way. In other words, we connect dots. If we look at 3 dots that looks or 10 dots that looks like a dog, then we see a dog, and that's how human eyes are trained to process. And I think that visualization, we just talked about human factors, that visualization is partly also at fault in perhaps inducing those failures. But that is all to say, there is a lot of work to do in this field and a lot of interesting things that one can, either challenge these existing methods, popular methods, to find the caveats, the holes, or to think about perhaps completely different paradigm that we need to be thinking about in the field. It's exciting time to be part of this field. So I think what I'm going to do, if that's okay with everyone, I'm going to cover as much as I can for the evaluation section until like in 13 minutes or so, and then we'll take a little break before we continue on. So for now, I'll do it. Oh, there's another question. Yes, lots of works have used attention weights as a tool of interpretability. Is it a proper way of providing interpretability? Oh, great questions, guys. It depends, is my answer, as we will see in evaluation. That while this fails this sanity check, again and again, what we will come back to is what's important to claim that you've achieved your interpretability is end task. Whatever you're trying to do, helping doctors or whatever. If the interpretability method and even this attention weights are helping to help doctors to diagnose patients faster or more accurately, then I argue that it's not a failure, that you could make this work. And we will talk a little bit about experiments we ran to further answer that question. But I don't think we have a conclusive answer there yet. We don't yet know whether in what cases we should be using the attention weights and in what cases we shouldn't be. Good questions. All right, I'm gonna do a little bit of evaluation section before taking a break. All right, now let's move to this very important section, how to evaluate interpretability methods. Thanks for everyone, great questions. So evaluation. Evaluating interpretability method is not as easy as tracking a mathematical metric like accuracy, right? But yes, we can evaluate them rigorously, as many folks in the field has done, and we can compare across them and across papers and applications. So here's 3 ways that you can start to think about how you would evaluate your method. This generally goes in order. So if you first have access to a method that you're thinking about using, or you're trying to develop a method, this is the order that you want to evaluate your method. So you first have no humans and test them on proxy task. And then you get some humans, but maybe not expert humans, and test them with a proxy task. And then finally, if you gain all the confidence that you can finally buy in perhaps some expensive experts time, then that's when you do humans with real task experiment. So let's talk about how you can first evaluate with no humans and proxy task. I think there's one question about ground truth. So these a few slides are for you. One way to do this, there are a few different ways to do it. The idea here with testing an interpretability method without humans and proxy task is to test the obvious. You can test hypotheses that should be true by crafting a ground truth data set. I'm going to give you an example of that. You can do the same thing with the real data set, the testing hypothesis. And finally, you can also do sanity check. It often include testing hypotheses that should not be true, like asking crazy questions. So let's first look at how you can craft a ground truth data set. And this is one of many, many examples that we saw in the literature. And this is one particular example that I worked on, and a data set that's been open sourced to help evaluating saliency methods or attribution method or attention methods, whatever you would like to call it. So how did we make this data set? We gathered the scene data, which just has the forest or kitchen or scenery. And we got this image patches from MS Coco, that like a cropped object, like a dog or a backpack and whatnot. Then what we did is we copied and pasted this dog in all scene images. Let's say we did that. What are we trying to do here is that by copying and pasting this corgi everywhere, I know that corgi is not important for predicting scene classes, because no matter what scene is, you have a corgi. And the model cannot, and we can quantitatively check this too, that model is not using corgi. So corgi should not be part of the explanation. You can also make this a little more complicated. You can make that corgi to appear in certain classes. So corgi always appears in kitchen, but not the forest. Is to make the corgi more important in some classes than others. So we are carefully controlling and arbitrarily correlation so that we can compare different models or different inputs. So let me talk a little more about that. So here with this data set, what we're trying to do is find false positives and evaluate false positives, and that only. So what is false positives? Your interpretability method said it's important, but model doesn't think so. And there are a few metrics that we propose, but let's talk about one of them, the model contrast score. So here we're going to train two models. And in these models, we're going to one classify scene and the other classify an object. And because they're trained to look at completely different things, we expect the contrast, the attribution methods, contrast on these image patches, like where the dog would have been, where the dog is, to be very, very different. So this is the case where I will give the forest picture with the dog to the scene model. And in that case, I know that dog shouldn't matter. And with metrics like this, you can quantitatively evaluate different methods, and you can make this score between 0 and 1 so that you can compare across different models and different methods. So takeaway here is that you can craft a synthetic data set for your domain, whether it is sequential data or tabular. And I recommend that you add typical challenges that you may encounter. Maybe that is a Spears correlation or domain shift problem, and see if the method that you're considering is doing the right thing. And this does not mean that just because you pass this test doesn't mean that you have the certificate that this method will work. It's in fact, you're still far away from that, but it saves you some time by maybe narrow down the number of methods that you're considering, and maybe iterate your methods, because if you don't pass this test, there's no point testing any further with humans. And there's a question about, do you also train with this data? Yes, maybe this is my past self already answered this question. Yes, you do. Now, second way to do this is testing hypotheses that should be true using real data set. So with the real data set, you don't have ground truth, right? So what you do is, again, testing what should be true. Here is an example of work that we did a couple of years ago. The claim of this paper is that we can discover patches of images that represents a high level, those which we call concepts. And say, given a police van, you have maybe wheel concept class, which is the first class on the right, and maybe you have a sky class, which is maybe less important, and you can evaluate how important each of these concepts are. So we segment the images, training images, and then do the clustering and evaluate them to see how important they are. So given this claim of, okay, you discover important patches, what you can do is that you can measure how prediction accuracy increases as you add the patches in the order of importance. So if you add the most important patches first, then you should see prediction sharply increases, and then you will see some diminishing return. And the graph should be the opposite, like mirror image of it, if you're adding it with least important patches first. And if you're randomly selecting patches, that curve should be somewhere in the middle. So, and that's what exactly we see. You can also do this in the other way. So instead of adding image patches that you order and discover or rank, you can delete those patches, and you should roughly see the same, actually the reverse curve from the prediction accuracy. Now, this is something that you're, again, testing something obvious. There has been lots of different ways to do this, and most of the papers that evaluates interpretable method hopefully is doing this. Here's an example where this work defined to claim to find a region that is smallest region of the image that alone allows a confident classification. There's actually another thing that they're trying to optimize, but this is one of it. And to measure those, they define a metric of saliency that details are probably better understood with the reading of paper. But with this metric, they're able to quantitatively verify that what they're doing is doing what they think they're doing. So again, testing the obvious. And again, this metric isn't perfect. One can select metric that is favorable to a method, but remember, this is just very initial check. Just because you pass these tests don't give you a certificate for this method, but it does give you a pass to move towards human subject experiments. Okay, apparently I didn't answer the question, Roman's question. Do you retrain here, yes or not? So I think were you referring to the beam? If you're referring to this beam model or the data set, yes, you train a model to classify scenes sometimes, and you train a new model to classify corgis or the object, and then you do that contrast. Now, you might argue, well, but that's not the model that I want to interpret. Well, it's not really that. This is sort of testing the one step before that. You're just testing whether this method shows you something that's truthful, even in this very simple setting. And again, if it doesn't pass this test, then there's kind of no point going on. And you can think about, imagine you can craft its data set. This is a particularly image domain, but you can do this with sequential data. You can do this with maybe tabular data, maybe electric health record data that you sort of made up, and do the same thing to test a couple of methods. And that's kind of exactly what we did in this paper. We collected a couple of methods and tested them under this metric that should be true. Hope I answered your question. If not, please keep asking. I think we can do this one and then take a break. So lastly, last evaluation for ways to evaluate without humans and proxy task, do the sanity check. This is often asking crazy questions, and I kind of love asking crazy questions. And an example of that is something that we just saw about saliency maps failing this sanity check. You can also do sanity checks not only for a method, but you can go a little more meta. So testing metrics for methods is what these folks did. And in this work, authors did sanity checks on many metrics that are used in saliency method and found that they are statistically unstable and inconsistent with each other. And remember that this line of work doesn't necessarily invalidate previous findings. it discovers some aspects that we might have overlooked as a community in the process of development. And because interpretability is a new field, and being critical about what we are doing is a healthy way to do science. So takeaway, being skeptical is healthy and productive. All right, before we moving on to next, why don't we take, say, 8-minute break? So we'll start at, I don't know what, 11:38, is that right there?
Exactly. Yes, exactly.
All right, we'll see you guys soon. Everyone get some coffee or water. See you soon. Thanks for coming back, everyone. We're going to continue and love all those questions I got. Please keep asking questions. Great. So next way to evaluate, we're going to talk about how to test with humans, but still with proxy task. So what is proxy task? It is a task that maintains the essence of the final task, and we'll see an example, but likely that you made up those tasks and the ground truth is known. And the benefit of this is that you may recruit humans who may not be your ideal users. Ideal users type of they're like doctors. They're expensive, but they can still represent some cognitive behavior and evaluation with this proxy task. So let's see some examples. Here's an example. In fact, I think there was a question about how to the ground truth with the human evaluation. I think this is one for you. I'm forgetting exactly what it is. Oh, there's a question. Let's cover this first, and then I'll go to the question. Thanks for the question. All right, so here's an example of conducting human subject experiment with proxy task. So here the goal is we're going back to that idea of failing sanity check. And here after that work of sanity check failure, we have this nagging question but there's a lot of papers that use these attribution methods or saliency methods and show that they were helping doctors, they're helping the domain experts. So maybe there's something here. Maybe there are some tasks that these methods are useful. So we decided to test that. How did we do it? Well, we made up this scenario where we intentionally inject bugs in a typical machine learning pipeline that machine learning engineers might encounter, such as you may have labeling errors or in the training data, or maybe you have a spurious correlation. And at test time, perhaps you have out of distribution data problem. And then what we did is we recruited truckers and asked them, okay, imagine you work at a startup and you're trying to sell animal classification machine learning model. Here are images, predictions, and the saliency map or attribution maps. Here we gave users the prediction label because it's just unrealistic not to. However, this is a confounding factor for our discovery, but still yet, as I will show you, we discover really interesting findings. Then we asked truckers, would you recommend this model? Having seen the prediction and explanation and the image, would you recommend this? Should we sell this model? If so, or if no, why? Was it a wrong or correct label or explanation? So here is another part that you can guess the answer for yourself. Here I'm showing you 4 models, one of which is trained with this input data distribution. So the input data here is fashion MNIST, black and white image. They're objects, not very high resolution image. Only one of these 4 models are trained with this image. Which model do you think that was trained with this fashion MNIST? And each column, I'm showing you different methods. Give me a second. And the answer is model A. Now, model A is, and if you guess there's something else, I understand it. And I understand you because I can't guess either. All these explanations, to be frankly, seems pretty reasonable. Yeah, there's a lot of D now. I'm seeing your answer. I think D sounds pretty reasonable, except D is trained with ImageNet, the natural images. And subjects thought the same way. They were uncertain whether they should sell this model or not, but mostly because of the wrong label, wrong prediction. And a lot of them actually thought explanation were as expected. And this is exactly a great example of where having wrong explanation can do more harm than good. Because while model had a bug, that it was out of distribution problem, that by giving an explanation, it was providing that false sense of trust. In another scenario that we tested, we inserted spurious correlation. So here, guess which one we are trying to classify. So this is one model, both are the same model. And we either are trying to classify the sea in the ocean, or we're trying to classify the bird. Which one do you think is spurious? And of course, we made up this data set, right? So we know that we copied and pasted this object into a particular scene or the other way around to make sure that spurious correlation holds. So do you think the ocean is spurious and we're classifying birds? Or do you think that birds are spurious and we're classifying ocean? Give it a second. And the answer is birds are the spurious. So we are classifying the birds. And this one, folks are actually still uncertain. So apparently they can kind of tell that something's off. And more importantly, most of the reasons why they were uncertain was because unexpected explanation, that they thought something was a little bit up. Oh yes, Yashi, I guessed it correctly here. I'm just starting to see the answers. So this experiment results gave us some hope. We were like, maybe these methods can tell you something about spurious correlation. So that's an example of evaluating human with a proxy task. Here's another example of doing something similar. So here, again, we're going back to the method that we briefly talked about, discovering image patches that are important and together form a concept, some high-level concept. And we did here 2 tests, and these are pretty classical tests, I would say. I've seen people running this test in many cases. One is the intruder test. What it is you give humans many images, and you intentionally insert one weird one, random images or random image patches, depending on what you're doing. And you ask humans, can you point out the one that's weird? And you compare that performance with human labeled data set, so something that you think that will achieve high performance. If these patches are in fact interpretable, that you would expect humans to perform pretty well. So we compare that. And another test that we ran is meaning test. So we asked, here are patches that our algorithm discovered. We liked them, and sometimes we did give them the patches we discovered, and sometimes we gave them random patches. And we ask, which one do you think is meaningful? And if they are meaningful, then can you put a name on it? Can you put an English name on it? Now, this experiment, to my surprise, more than half of the subjects put the same English name. So I think in this case it was a human. And if you count the top 2 terms that they wrote down, 77% of people said the same thing, which is kind of a good evidence for this data set that we tested, at least, that discover concepts are coherent. Now I remember there are some questions that I was going to visit and I forgot. I'm going to go with the reverse order. The size of the object could be the reason. Oh, you mean the spurious correlation? You mean like size of the object was big enough to kind of get? Yes, in fact, there's some follow-up work that we're doing on that spurious correlation, where when we made the spurious correlation a little more subtle, say it's like a line in a medical image, or it's more Gaussian blur, that we made it spurious correlated with the classification, it's actually a lot harder to read that out of saliency maps. Yeah, good question. And I think there was a question that I was going to cover and forgot. Yes, I think that was, oh, there's another 2 questions. Okay, let's go through that first. So Puan asks, what is the bottleneck of applying interpretability method on graph neural network? I don't particularly cover this in this tutorial, but there has been many methods to develop interpretability methods for GNNs. And there's one, I believe, came out of Brain that provides the synthetic data, like the dog, corgi, and the scene data that I talked about, very similar synthetic data for graph neural network to confirm that their method works. So there's lots of interesting work going on there. There's a bottleneck. I don't think there's particular challenge. I mean, it's more complex, but is it present particular bottleneck because of the graph neural network? I don't quite believe that to be the case. I mean, it's harder, or maybe easier. That's also to be discovered. Another question goes, it seems that a lot of interpretability techniques consider classification scenarios for analysis tasks that attempt to automate a human process for improving understanding of some task. How can interpretability be measured other than evaluating with humans for analysis tasks that attempt to automate human processes? I'm curious what you mean by why would you need, I see. So are you talking about you need interpretability before you launch this automation? You want to make sure that this method actually works. Perhaps that's what you meant. If that's what you meant, and you're specifically perhaps thinking about non-classification scenario. I mean, classification scenario is a great example of automating, potentially automating human process, right? So if you have, I think I've seen some networks that automatically classifying recycle given a camera, let's say, and that's a great example. All right, yeah, thanks for, yes, so that was the question. And in that classification case would be kind of amazing to automate this and perhaps save people to do something more interesting than classifying garbage. In that case, I think similar methods can be used to sort of perhaps analyze errors. Typically, what kind of, it gets plastic bottles always wrong, or maybe it gets some, you know, if the can is dirty, then it doesn't get it very well. I think those methods are completely applicable. Are there other things? And I think when it comes to automation, I think one important thing to consider is humans and machines will make different mistakes, right? Because they're not identical. And you want to be very clear about what kind of mistakes are okay and what kind of mistakes are not okay. And that carefully, really, really carefully test that before you launch the product or launch and start the automation process. And I think perhaps interpretability methods and trying to understand deeper into how models reason is a great idea, but you should also do very rigorous testing with perhaps synthetic data, better yet with real data to test the failure cases of your system. Yes, and another question, which methods can be potentially used for deep learning model debugging visual tasks? Till now, you do not really see, I do not see anything suitable for all represented here. So hopefully we'll get to that in the method section. I know that we're, yeah, we might actually, I should have said this, we might run a little over time because as I prepared this slides, I wanted to, I want to also talk about this. I also want to talk about this. So we might run a little over time. Yeah, so hopefully I'll answer that question, Roman, later. So that, and we'll move on to, so takeaway for this, coming back to testing with humans with proxy task. Proxy task can be an effective way to evaluate a method, often before running real expert on real tasks. Really. And finally, and the golden way of evaluating interpretability methods when you can, and this is a must if you think that your model is going to make high-stake decisions such as medical, then testing with humans or real experts on real tasks is crucial. In fact, without it, you shouldn't really be thinking about deploying any of these models without doing something like this. So some folks had worked with pathologists to find, they developed this refinement tool and see if they can increase user trust and utility of finding the right medical images for their analysis. Another work is where they worked with this anesthesiologist by providing the risks of different factors that one might have post-surgery. And these are all really great work to pursue with testing with real experts and on real tasks. So will we? I think we might run out of a little bit of time because now we're gonna cover some method section. Before that, I'm going to reiterate what I already said before, that interpretability is not a new problem. And, because I'm going to focus more on the reason method and going forward, but I really wanted to reiterate that it isn't really about deep learning. And I've met a lot of people who think that interpretability problem came about because of the deep learning. Not true. There has been many great work in expert system in the 70s that already carefully thought about this interpretability question. And if you want to read more about this type of methods, there's a great paper written by Alex who can give you a great overview of comprehensible classification models on a position paper published in 2014. So with that, we're going to talk about interpretability methods. There are lots of different ways to categorize these methods, but here is one way to do it. One, we're going to talk about explaining data. So let's say you have some quality function of explanation Q. You're going to try to find explanation given human data and task such that you maximize that quality function. You can build inherently interpretable model. You're jointly optimizing, or more likely that your model is the explanation and they're the same thing. Or post-training interpretability methods, which we talked a little bit about before. Given a model is fixed, your goal is to find that explanation. Someone asks, can we get the PPT, please? Yes, it's a keynote, but I'll give you the PDF. Absolutely. So first of all, let's dive right in. The understanding data is very important. And if you've worked in a practice or try to apply machine learning in some real data, you probably know this to heart, that understanding the data is often much more important, and the problem stems often from the data and not the model. And one way to help you interpret the data is a process called exploratory data analysis. And what that means is an approach of analyzing data sets to summarize their main characteristics and blah, 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 and such that you can know something beyond the formal modeling or hypothesis testing tasks, something that you can know beyond that. So what are the examples of that? Oh, let me go through this one real quick. Question about what is the interpretability telling if the model built by total data versus random is 25% of it shows the same performance, or the different, let me just try to parse this for a bit. If the model built by total data versus random, 25% of it shows the same. What do you mean by same? I think I need a little bit more clarification, Songsu. If you don't mind, what do you mean by total data versus random? Do you mean random data, random label? Yeah, so tell me there in the chat. We'll come back to it later. All right, so coming back to exploratory data analysis. So what is it? Let me give you an example. Let's think about this data that we have some nice two-dimensional data. We have some blue class and we have some red class. One way to do exploratory, the most simple way to do it is to find descriptive statistics. So you find some mean value of class, but the blue class, and mean value of the red class, and maybe you can find some standard deviation too. And of course, data can be a lot more complicated. There's a lot more to it than just the mean and standard deviation. So is there a better way? There are many, many different ways, but many methods that we already know can be used to do explorative data analysis. And there are cases where examples are more powerful way to explore your data because your data sets are more complex and context is important. For example, if you have images, averaging over features won't work. But showing you this one picture of two different dogs could be more powerful and provide better context. So that sounds good. But what about this little minor groups next to this big clusters? We kind of want to know about them too, because chances are these little groups of people or data points are often the problem makers. If you go back to finding some errors in your model, very often I find myself looking at this like a small group of data and say, where are you? Where have you been and where have you come from, causing all these problems that I saw that I didn't expect. So here's one way that we thought about this problem years ago. And the idea is that we not only learn prototypes, which is examples in this big majority class, but let's also think about criticisms, examples from the data points that you would criticize you over if you had just picked prototype. So if you just picked prototype, then these are the data points that I'll go show you and say, look, you missed these guys. And the way that we do it is use a particular metric, and the process goes like something simple like this. we fit a distribution over P, the prototypes, on the data points. And then we fit another distribution Q such that it fits this difference between the data points and the P. So the difference between what you have already explained with prototypes versus what's left in your data point. And to do this, you can do this in many different ways. You can use different distance metric, but we use something called MMD because it's a very simple, elegant way of taking the statistical measure between distributions. And you can measure this using samples. So we do that. Here's a question. An interpretive method called prototype based, is it correlated with the concept of prototype in few-shot learning? Perhaps, yeah. I think there are a few different ways to prototypes are defined. In fact, in some classical case, prototypes are defined slightly differently, that it's not an actual training data point, it's some made up data point that would describe an overall distribution. But in machine learning, we define it slightly differently. But I guess it depends on how you define it. But correlated, I actually never tested that hypothesis, whether that we select these prototypes here and are they good for and best for few-shot learning. Perhaps under some metrics, but I haven't personally tested that hypothesis. And here are some examples that quickly I show you what prototypes and criticism look like. Here, prototypes are dogs with their faces facing forward, kind of typical dog pictures. And criticisms include black and white picture, or dogs in costume, or dogs kind of looking away. Thanks Sungzu for clarifying the question. How to interpret the performance difference between model of training a total data set versus 25% of it if the smaller one is just randomly selected? Oh, sorry, it's got, okay, cool. Interesting. I think if you train two models that are based on different data sets, those things can be completely different model. I think that comparing it, I guess it depends on the goal. Your goal of comparing it is your goal to find the best 25% such that you can achieve the same accuracy. In that case, maybe comparing it is interesting, but it really depends, and we would have to know what the goal is. Yeah, it would have to be think a little more about that. But interesting question. Maybe you have something you've been thinking about Lorry ticket hypothesis, which I'm going to talk about briefly later on. Chiliang asks, can we consider theory of machine learning as a kind of interpretation? It might differ from the definition of interpretability here, but it also gives some insight into the models. Theory of machine learning. Yeah, perhaps. I think that, I'm thinking like VC dimensions when I think about, or empirical risk. I think that there are some principles that apply in and impact interpretability work as well. However, I am not 100% sure that if, let's say, we know the 100% about theory of machine learning, that interpretability will be solved. I don't think so. The reason is that every human is different. Every application is different. What's going to work best for you is going to be different and will continue to change as we use machine learning for different things. I don't think that one principle is some global generalizable principle is going to solve this all and once together. Because the fact is, psychologists try to understand humans for ages, right? We're very complex systems. And yet we still don't know, and I don't think we ever will, know how to mathematically define a human. If math or the theory is the thing that that would have solved all this problem of psychology, for example, then one, humans would be perhaps much less interesting subject, and two, they would have happened a while ago because we've been trying for centuries. Perhaps some aliens have the answer, but we don't, and I personally don't think they will ever have that. All right. Ooh. Okay, yes. So let's move on. And here's another very important family of exploratory data analysis that comes from visualization community. And I'm not an expert to talk more about this, but here is a great review of position article on many exploratory data analysis results in research, journalism, and education, and many others. So I highly recommend you going to this site and look for it. If you look for some of the first author name, or I can share this keynote for you to have a look. This is collecting a lot of visualization research in the history. It's not just this set of authors' work. I find it very informative. So second, next category of interpretability method, let's talk about building inherently interpretable models. Here, by inherently interpretable model, I specifically meant that when model itself is an explanation, which means that we don't need to approximate anything. We don't need to do anything separately. The model itself becomes the explanation. So here's an example. Here's again our favorite picture, blue and red class, very unrealistic, but helps us anyway. One thing you can do is you can build a rule-based system. So for example, you can say if the feature 2 is less than 0.3, then I'm going to predict mostly the red class, and so on. You can keep dissecting this space until you get accurate classifier in this case. And in this case, the model is explanation. There's been a lot of work, decision trees, rule lists, and rule sets, and many others. And sometimes this is the right fit and can give local explanation, meaning that you want to explain this one data point, and you can get that explanation exactly in the way the model think. But as we saw in an earlier example, like decision tree practice, this may not always work for everyone, since as the tree gets complicated, even like 5 depths, the thing we saw, human cognition load becomes very high. But regardless, these models are the right model for many applications and useful. Another way you can build inherently interpretable model is to fit simpler function for each feature. So for instance, you can fit this fit this blue and red function curve for blue class and red class for feature 2 and feature 2 alone. And you can do that for same for feature 1, feature 3, and many others. And there is a class of model that has this property. It's called generalized linear model or generalized additive model, where if you think about linear model as just an addition of each feature with some coefficients in front of it, generalized linear model is putting this hat on y, so put a function g so that you can learn a little bit more complex function. You can also put a hat on each feature, f for each feature, to make it even more expressive model, but still the features don't really interact, and you can pull out a function, exact function that this g of y is relying on. Or you can make it a little more complicated by encoding also the interaction between features too, and that's called GA square M. Another important method is to use examples. You can pick examples. You can pick examples for each class to simply and powerfully describe this is a dog class and this is a cat class and so on. And the reason I've done a lot of work in example-based models when I was in PhD, and I just find over and over again how powerful examples can be. And there has been lots of cognitive research on how human experts think in examples. And context is really important for humans to build that rich but efficient mental model. Like in rescue scenario, search and rescue experts often use this type of reasoning process to make a decision quickly. Another way to build inherently interpretable model is to build mimic models or model distillation, that it's a smaller, more interpretable model that performs as well as the initial model. So then in that case, you can just throw away the complex model and use this more interpretable model where the model itself is explanation. And so these are the simpler model that walks and talks and barks like the complex model. So you can distill initially on interpretable model like neural network to tree or forest, depending on what works for you. And bonus is that by doing this is that you can demonstrate that you can build an accurate model without the interpretability goal, and you can match the performance of that so that you can explicitly show that there is no trade-off. And more recently, there's an exciting line of research based on lottery ticket hypothesis. the idea here in this paper is quite simple and quite fascinating. So you can have a randomly initialized dense neural network, and they always include a subnetwork that matches the accuracy of the original network. And this is really exciting because perhaps if there exists such subnets, then maybe there's more principled way of distilling our model. We talked about theory just now, and perhaps there is some way to theoretically prove that some interpretable model inside of this neural net exists. I don't know. Lots of interesting work has been followed too. So lastly, perhaps somebody was right that we may not run over time. Lastly, we're going to talk about post-training interpretability methods. And again, our favorite example, blue and red. So in this scenario, what happened to you is somebody gave you a model. Somebody gave you this curve of red and blue, and you're like, okay, fine, I have to work with this. And you cannot change this model, say. And this is typically a case for high-stake decisions. The first thing you should try to do is to build an inherently interpretable model where the model itself is an explanation. But a lot of cases in application, real world application, maybe in a big tech, that we have models that many people built and iterated over decades. And in that case, and sometimes we have not just one model, we have models of models, systems of systems. And we know it's pretty obvious to me that we cannot replace that whole thing with one model, one interpretable model. Right? Replace like years of engineering effort with one model. So in that case, you resort to post hoc interpretability methods. So you have these curves, somebody gave it to you. One simple way you should start thinking about doing as a start is to marginalize out the particular feature. So all data point collapses to on the line of the feature 1, F1. And this is type of ovulation test. So you're training, say, a model without that feature and data and see how that impact model's performance or certain behaviors. But of course, this is expensive to do, sometimes not possible because maybe it's too big and it takes too much time. So smarter way to do ovulation tests is use influence functions. This is from 2017, where they define the importance of a training example to be how would employer's prediction change if a training input were modified. And here's an example. Let's say you have two models, one is SVM, the other is Inception. You have this one image of fish, and these are training images that was most helpful. And what sort of makes sense here is that Inception has more rich representation of the fish and probably more, maybe more accurate, and therefore it is able to grab those actually same fish with the test image. So this is one way to do ablation test. Second way is you can do sensitivity or fitting linear function or gradient-based method. So this is type of the saliency method that we just talked about. And in fact, line method, the famous line work is doing exactly this. You fit a linear curve in this complex decision boundary around this particular data point that you want to explain, and look at this linear function as a way of telling which feature is important. And in this case, the importance is defined as what would model's prediction change if this feature changes in an infinitesimal level, and that's the definition of gradients. And here we talk about lots of saliency maps. We already talked about that, IG, smooth grad, and many other work. You can also use optimization-based method. What do I mean is you can choose a loss function that meets that desiderata. We talked about how you define what means to be interpretable for your end task, and you can directly optimize for that. So for example, this is the work that we already talked about, getting for small sufficient region or smallest destroying region, and you can directly optimize for that. And there's other ways to define that loss function, like get me mask such that the mask does a particular thing. I'll go to this question quickly. When the mimic model's behavior are similar to the black box model, and we always explain the mimic model, how do you ensure that if we're some potential threat in the black box model not detected that we deploy the box? So in this case, if you can build a distillator model that matches your black box model, you should throw away the black box model, right? There is no reason to use black box model if it achieves the same goal. And of course, that should be considered. That should be also, you should do a lot of testing to make sure that the data points that this black box model got it right or wrong, those behavior still is true for your mimic model. So yeah, you cannot rely on the mimic model just itself and gain some trust about this black box model, because those two are different models. And yeah, she asks, is uncertainty estimation also a way for interpreting the model? Yes, it is a way to gain insight into how models think about its own prediction. However, like one caveat there is that neural network in particular is notorious for having bad confidence estimation. And I did this work in a couple years ago about how can we improve that measure of confidence. It's a paper called Trust or to Not to Trust. And we were shocked to find out, perhaps the things will have changed now. We're shocked to find out that there aren't that many work that talks about how to improve this confidence measure. And perhaps Bayesian method should be here to save us from there, but that was the state of art a couple of years ago. Another question, can an interpretability method be used to select a model over another model selection? Oh, absolutely, yes. And we'll perhaps talk about that in a bit, and when I talk about introduce TCAP. And now I'm confident that we're going to go over time, and hopefully that's fine with everyone. It's fine with me. All right, so we talked about optimization method. Now another important method, I think someone asked before about counterfactual explanation. You can absolutely do this too. And typical definition of counterfactual explanation is find me an x prime. I have x, and find me another data point x prime that is as similar as possible with my x that I'm interested in explaining, but with different prediction. And as you can imagine, you can put down a loss function to explicitly find this data point x prime, and that's what Waters et al. And others did. And Anna Rusik's work extends this framework for non-differentiable network like trees. Also, Amir's work, Karimi, Amir's work also introduced us some of the general framework, really interesting framework to how to solve this in general sense. It's also important to note that some of these counterfactual explanation literature uses the causal inference framework, but a lot of them also don't. Which one is right is, again, depending on your, you should do your testing with your end task to determine which one is the right fit. Just because it's causal doesn't mean that it's going to work better, as hopefully now it's obvious. Cool. And another important direction is using game theoretic approach. So game theory is typically described as if we all work together to play and we have a gain, how much each player contributed to final outcome. And in the context of interpretability, you can think about this as average marginal contribution of a feature value across all correlations. So here are all different ways that this game could have gone, and what is my marginal contribution. And here gain is defined as the predicted value of x minus the base value, which is just average over all prediction. And Shop, of course, introduced this nice framework to combine and unify many of existing methods under this Shapley value framework. And the cat appears again for us, and it says, are these all methods definition of importance give me similar answer typically, or which one, how do I know which one I choose? Well, here's a very simple example where I can show you that very simple difference can lead to very different intuition. So let's look at two different ways. One way to find feature importance is to look at just dominant features. I have a group y equal 1 and y equal 0. I'm curious which feature were dominant just by looking at the data points belongs to each class, each predicted class. So here we have two models, blue and green. And when I look at blue and green and look at their dominant features, they say similar thing. if I have a high value of x1, it looks like I belong to y equals 1 group. If I have a low value, I am in the y equals 0 group. Sure. However, let's now change the definition of importance and now we're looking at whether the feature is sensitive. So we're looking at the first order derivative as we have in the attention map. Now, in this case, these two curves that was seemingly look very similar before gives you very different answer. So now, because we are looking at the slope, the derivative, so it's like a tangential curve on your black and green curves. When you look at blue, because there's no data point that has x1 being high but class 0, your derivative is 0. So if you're just looking at the derivative, first order derivative, you might be convinced that feature x1 is not important. And of course, neither of these imply any causal relationship. So which one is the right thing to do? Well, it depends. Again, hopefully now enough repetition that you would know that you really need to test with your end tests after doing all the synthetic data and proxy tasks to see which definition of importance work for you and for your domain, for your goal, and for your users. Another important thing to know about this feature-based or sensitivity-based methods like SHOP and LIME is that there has been a large literature that shows the robustness of these explanation could suffer. So here's a simple example of a 2-layer network with 2 features, the green and purple. And if you zoom in this particular region, you can see that 2 data points that are very close to each other. So to humans, these are very similar data points, can give you very different explanation. And purple and blue curves are the opposite. So why is this a problem? Maybe this is exactly the right explanation for that local region anyway. Well, the problem is that when humans see 2 similar data points producing inconsistent explanation, and you do that many, many times as it's shown in this picture, then they very easy to completely lose trust in the explanation. So despite being perhaps accurate under some definition, however, it wouldn't be even accurate if you have very rugged decision boundary, then this explanation methods would really fail to get adopted by those experts. So those are some of the problems. So finally, now you might ask, why do we talk about this feature? Why do we constrain ourselves to axis-aligned features, which is kind of a lot of times arbitrarily defined? Like pixels, each pixel is a feature, but if we combine them together in a certain way, then we can make something a little higher level, like meaningful concepts. Like if you combine features, then we can say something like, here is dog tails concept, here is human face concept, and so on. So another way to interpret post hoc a fixed model is to use high-level concepts. In other words, if you say you're a layperson, you own a pizza restaurant, but you heard about machine learning, so you bought some services off of some company, and you train a model to predict whether this pizza is going to be popular this summer or not. Now, you have 2 choices. You can either get this explanation of pixels that look like it's highlighting the tomato, maybe it's highlighting the wine behind it. Would you rather get that, or would you rather get some quantitative explanation of the high-level concept that it's better for you to act on? Because if I know that tomato is more important by 0.8%, then I better go get some better tomato, because apparently that's what makes pizza popular. In other words, humans, for some use cases, it might be most useful to have quantitative explanation how much a concept is important for a prediction, even if that concept was not part of training. So I will talk a little bit about our work to answer this question. It's called the TCAV, testing with the concept activation vectors. The method is pretty simple. I can explain it in a couple of slides. And to explain that, I'm going to use this example of how important was the striped concept to this zebra image classifier. First of all, you might ask, okay, the concepts sounds good, but how do you even define concepts? What is this? Well, we do the simplest possible thing. We define concepts using a vector, and we give it a name called the concept activation vector. And to learn this CAV, you need a couple of ingredients. you need examples of concepts, and you need some random images. And we assume that you have access to the activations of the network that you're interested in investigating. Then what you do is you train a linear classifier to separate these activations from the random image activations to concept image activations. And you get the vector orthogonal to that decision hyperplane, and that is your CAV. So what is this CAV? Well, it's just a direction that points from random activations to concept activations, and that's it. And of course, this is not a new idea. This idea has been studied many times in the history, and there has been shown again and again that there exists this semantically meaningful direction in the activation space. So that sounds good. You have this vector now. How do you get that quantitative explanation or the TCAP score that I talked about? The idea is pretty simple. Here, we define the importance as, again, the sensitivity. We're going to, I'm asking to tell me how sensitive the prediction is when I change the concept a little bit. So for example, if I make this zebra picture a little more stripy, how much would my prediction of zebra change? If it changes a lot, it's an important concept. If it doesn't, it's not an important concept. So we can find this directional derivative, which is a very common thing. It's not, of course, nothing that we invented. It's just a derivative with respect to this vector instead of a feature. We do this for many, many zebra pictures, and we aggregate this statistics using by just simply counting how many zebra pictures out of 100 that has outputted zebra. Sorry, I think my laptop is running out of battery, so I'm going to quickly plug that in. Would help. Hopefully that will help. So in TCAP score, you're just calculating the ratio with zebra pictures that outputted the positive directional derivative, meaning that having more stripeness helped prediction of the zebra. And this score is, of course, always between 0 and 1 so that you can compare across model. Now, I remember there's a question about how do you compare interpretability to choose model. And this is one way you can do it. Let's say you don't want some concept to be sensitive in your model, and you have trained many models, and you have to make a decision. You can use something like this, the score between that is normalized across models, in order to select model that meets your criteria. A question that you might ask is, okay, so this CAV business that you talked about sounds fine, but you know, in high dimensional space, funky things can happen, like adversarial examples that we all know about. So how do you know this CAV is legit? There's many ways to do this, but one quantitative way of validating the CAV, at least that it's not giving you accidentally high sensitivity, is to, instead of getting one CAV, we're going to get many CAVs. So because you can learn CAV using random set of images, you can plug in many sets of random images as many times as you want and get TCAP score for the same target many times. Then what you do is you calculate the distribution. You pretend that those samples are coming from a distribution, and you calculate the statistical difference between that and CAV scores from random CAV, where CAVs are gotten from random images versus random images. And only those two distributions are significantly different, then we use those concepts to explain. So here we have some cute results in the paper, but instead I thought it would be much more fun to talk about real results. Like since this paper came out, other folks had done amazing experiments by using this TCAV. Here's a work came out of King's College London, where they jointly trained generative model and classification model to classify presence of coronary artery disease. It's like a heart medical images in the slide. And because they had a generative model, they could also use this CAV to generate images with different concepts. So here they've used the CAV for left ventricle to generate different images. And here's what they wrote in the conclusion that made me very excited. They wrote that interpretability using this known biomarkers allows the model prediction to be placed in the context of current medical knowledge and clinical decision-making guidelines. And this is exactly why we were excited about when we first invented TCAV, that this is helping users to speak their own language where their own expertise are grounded, instead of making them having to speak computer's language, pixels and whatnot. Quick question by Daniel. Do adversarially robust model improve the results of methods for interpretability? For example, in not robust models, counterfactors could be just noise, while robust models might not be. There's a lot of discussion around that, and I think there's a work by Alex at MIT that claims that this to be true. I think there's a lot more work to be done. So for example, how do you, in what definition of robustness and under what definition of interpretability that the following seems to be true. But intuitively, what you're saying, Daniel, does make sense, that perhaps you can sort of remove those many adversarial directions that may exist in the network. However, that doesn't guarantee you that there are non-adversarial directions or some other way that it could fail that isn't previously known to human that might still happen in robust models. Here's another work that came out of DeepMind who extended TCAV for RNNs. This is a sequential data where they explored different ways to define CAVs in this sequential electronic health data. And they tested it with acute kidney injury data set too. There's lots more work in the medical example, radiology and radiomics, and many others. My favorite work, one of my favorite work, is Eric's work of using TCAV for interpreting storm. So there's a classification model that categorizes storm to category 4, category 3. And Eric used TCAV to explain that model. And I actually met him in person after some talk in a conference. He came over and shared his work with me, where he also shared this wisdom that he had to make sort of the distribution of his training images, which is black and white, satellite images, to be similar to his random images. Otherwise, the embedding space didn't quite work out for him, which is a really important lesson. Here's a question. Should we adopt representation of a concept for automatic extraction of ACE, depending upon modality being processed, to increase meaningfulness for users? Depending upon modality being processed. I think what you mean is, I think maybe what you mean is like, depending on whether modality, I can mean a lot of things. So maybe what you meant is like, whether it's image or audio, or like maybe audio and image, maybe language and image. Depending on that modality, should we adopt that representation of concept? Yes, absolutely. If you have multiple modality that can co-inform the formulation of CAV or concept calculation, absolutely. That's a good idea. There's been other work at Google applying this for language model. And and if you might wonder that, well, what if there are concepts that are compounded? Like you have strapped images, but all your strapped images happens to be t-shirts. Then doesn't it also learn t-shirt? Yes, it might. Yes, it will, in fact. And there's different ways to distinguish or rule out, tease out this compounding vectors. One, you can use causal analysis. This work in Amazon is specifically using instrument variables, or you can do concept whitening. This paper came out of Cynthia's group. You can also use this idea to debug. This paper actually shows a lot of other interesting results, but one way that I was really excited to see is you can actually do some action based on information given by interpretability methods. There has been a few extension of TCAV work that I'm going to briefly cover. Here we already talked about ACE, discovering patches that are automatically discovering the concepts. Here are some interesting ways, and the way that we do it is, again, we segment the training images into patches, we cluster them, and discover new concepts after rigorously validating them. And here's some examples that I like. The middle one, Jinli Kisha, it was able to carve out that very complex boundaries of humans. So the third column there is like two humans, one human's arm maybe, and then one human's face. It was able to carve out that complex boundary, which is pretty impressive, and identify it as most salient concept. You can also discover complete concepts, because you can discover many concepts, but if you never know when to stop, then that's a problem. So this is work where we define a completeness metric to be similar to PCA vectors, PCA, and under which you can kind of use this idea of decomposing the activation space into vectors. And if those all vectors span that activation space, then we have a completeness. So there's one way to do this too, so you know when to stop. You can also train a generative model to produce countervectoral concepts. So the goal here is, for example, if you have skin images like skin sample pictures like this, and doctor asks, why is this skin region melanoma? Then you can produce multiple counterfactual generations of how this picture could change in order for the prediction to change. So this is counterfactual explanation for concepts. We've also done train the model with these concept labels to begin with, so that each neuron in some bottleneck each represent the concept. And the nice thing about doing this is that you can interact and control the model to some extent. So you can maybe ensure learning a concept that you know it's confounding and you know you want to zero out, like you don't want this concept in your prediction. You can intentionally include that in your model so that you can zero out in the prediction time. And we confirmed this finding that we can improve the performance by having this interaction. Another work that I'm excited about that's ongoing is to combine TCAP and IG, integrated gradients. So integrated gradient is about integrating in the path of images that with the different alpha value. But here idea is again pretty simple. We can integrate over the path of CAV so that we can offer both globally and locally consistent explanations. And with that, you can do something like this. So let's say we talked about zebra a lot. We know that stripes are important for zebras in general. But what about this zebra that I took a picture of from far away? Well, I didn't. It was ImageNet somewhere. Somebody did. From far away, the zebra stripeness doesn't really pop out. Instead, zebra kind of looks like a horse from far away. So you can kind of see this concept of zebra from far away. Horse concept is high, and as you zoom in on the beautiful stripeness of the zebra, you have stripeness concept in higher level than others. And the fact that we are able to get this amount of granularity is very encouraging. A question, this might be a naive question. Is there a number of concept vectors a crucial hyperparameter for interpretability? What is the qualitative description between them? Number of concept vectors. I think that this is one of the reasons that we worked on the completeness work. And here we're trying to solve that question for you. And in fact, even in ACE, we cluster these. You can cluster this activation using many different clustering methods. If you do k-means, the vanilla k-means, you have to specify the number of concept vectors, how many you want. However, there's like methods like dbScan where you don't have to specify that hyperparameter. You specify some other hyperparameter, but it doesn't explicitly make you decide that number. And same here. Is it a crucial factor for interpretability? Yes, and I think that that's another way that you could use the evaluation method that we talked about to decide. For instance, if your goal is to make this really fast, but you are willing to make this explanation a little more approximate, then you can optimize that hyperparameter to serve your goal the best, right? Maybe you want to learn small number of concept vectors. But it's faster, it's simpler, so that you can just kind of go. And if that's your end task metric, then it's something you can also optimize for. Good question. So with that, we talked about 3 different interpretability methods. So remember, it's a small subset of many great work that's going on in the field. We talked about explaining data. We talked about building inherently interpretable model. We talked about post-training interpretability methods. Here's some work that I'm excited about that I didn't cover here, but important. Doing science. I think this is This is such a great, interesting line of work. So a few years ago, there has been discovery that neural networks, CNNs in particular, are sensitive to texture. If you give a cat shape with elephant texture, that neural network thinks it's an elephant. And the way that these folks are studying neural network is studying neural network as a scientific object and kind of doing this probing and hypothesis-based testing to discover something about this complex object. And follow work as well to really dig deeper into this question, and where they discovered that CNNs are actually learn shapes as easily as texture. There's a lot of components at play in this bias. Another work that by Crisola and others to inspect each and every neuron to find, for example, what are the patterns that highly activates that neuron, and trying to study again this object of a neuron in neural network as if it's like a complex object that naturally exists in the nature. And this work is not only interesting but also really beautiful to look at. Network dissection from many years ago also try to see what sort of concept each neuron learns. Really interesting line of work. So that's the wrap. We talked about what and why and what, interpretability. We talked about things to be careful when using and developing interpretability methods. We talked about evaluation. We talked about many different ways to pursue interpretability and their examples. And I think it's an exciting time to be in this field. And yes, interpretability is a hard problem. And yes, we often encounter computer scientists who are uncomfortable with this fact that humans cannot be defined using math. But my question to you is, which side of the history would you want to be? Would you want to help steering this powerful technology to become something that we are proud in 20 years? Would you want to help layperson to use this power technology as well as privileged person like ourselves? And would you want to try to do the right thing, even though it's not always easy? I think it's an exciting time to be part of the right side of the history and try to tackle this hard but very important problem of interpretability. Thank you.
Thank you. Thank you very much. Thanks, Dr. Bin, for the very insightful and amazing lecture. So when we are waiting, because we are running out of the time, but we can let the audience type.
I can't really hear anything, but I could.
So when we are waiting for the audience typing their final question, I have a general.
Sorry, I can't hear you, Hyungi.
Oh, you can.
If you're typing something as something important, could you type in? I'm sorry.
Okay.
Oh, in the meanwhile, maybe I'll answer this question if that's okay. Alvin asks, how do you, I can't read. Let's see, how do you, let me copy that. Okay, I can't, it's scrolling back and forth. If somebody can help me to get that question, that would be wonderful.
Can you hear me now?
Thank you, thanks everyone.
Hello,
Apparently I can't really read it. It's possible it's my speaker problem. But if everybody can hear Hyungi and not me, then just go ahead. Okay. Thanks for the question. So Alvin asks, how much do you think the model failing to behave like human reasoning, interpretable, attributable to the intrinsic property of the model itself, or is it more towards the data? I think it's both. The fact that why is the neural network so complex to understand? Oh, everyone can hear him. Okay, I'm sorry. I don't know what's going on with my laptop. I think it's both the complexity. Why is the model failing to behave like human? It's both models' biases and in fact, even we don't understand how human brains work, right? If we can, maybe we can build a model neural network that thinks and acts like human, but we don't know that yet. So perhaps it is both the a lot of architecture biases that we're building in a mathematical model. We don't even know if math is the right tool to think about it yet. So it's all, and also the complexity of the data and their complex distribution, and also our comprehension limitation, right? If we are able to think in 10,000 dimension, we might be just understanding neural network like this, right? But we are not. There's a question. The current interpretable AI seems to focus on computer vision. Is there any way other field? Oh, thanks for asking the question, because I just saw, let me see. I just saw a great review paper just came out, hot out of press on Twitter, that hopefully I have slides. Okay, so here's an incompleted slide I wanted to include, and then I didn't. Here's a slide. Here's a survey paper that just came out by Andreas, who reviews post-hoc interpretability methods for NLP, and there are many other survey papers that you can look at. This radiology paper that's written by folks on reviewing all the interpretability methods for radiology too. It's super interesting. Are there explanation methods robust with respect to model initialization? I think there's multiple questions going there. Oh, actually one, yeah, so multiple questions going there. So if you reinitialize the model, chances are there are going to be different models. And what does it mean to have different models and have some robust explanation? I think that again depends on what you're trying to do. Are you trying to find an explanation that no matter what you do to initialization and retrain, that you're going to get the same reasoning, the rationale behind the model? I think that's a very difficult. I think as soon as you retrain the model, something might have happened, and all the explanation that you had in the same model architecture with same data, you have to be skeptical and rethink everything, I believe. Thank you. General question: what is your suggestion for students trying to apply interpretability within physics-related research fields with strong principles? Oh, I love it. First of all, I'm really excited about science. I've been thinking a lot about how we can apply these interpretability methods for science so that we can discover something new, perhaps something we didn't know before from superhuman network that can do things better than humans. And the first thing that I would recommend anybody to do when they're trying to understand a model is to do the simplest thing first, right? So descriptive statistics, applying simple existing well-verified methods like k-means or KNN. Just start simple. Ovulation test, if you can do it. Retrain the model, do that first before trying anything fancy. And if that all gets you to some insight, and that's really the time that you start, only the time that you should start thinking about more complex methods. Like maybe you want to train graph neural network to interpret that graph neural network and so on. Good question. Most examples in the talk are computer vision. Those methods may not fit well. I would like to have comments on, yeah, interpretable. So the question is about what about NLP? These are all mostly overfit to computer vision. Absolutely agree. So I think one of the interpretability field is overfitted to computer vision, and I think it was an area that was kind of easy to start, and perhaps because of that, we have phenomena like the sanity check failure, which is the downside of selecting and really digging deeper into this one area. And I think it's really time to pull ourselves back and think about other modalities like language. There's a lot of work in NLP too. I think a few work that came out, again, look at the survey paper to have more comprehensive review. But a few work came to my mind and that I liked. It was where the attention models, typical transformer style attention models, was proven to be not as interpretable as you think. And again, I think the TLDR in that paper, search for is attention really interpretable or something of that kind. I think it's written by Sarah. The conclusion there is it really depends on the definition of importance of your feature, like tokens, and depending on that, the attention mechanism may not serve you well. And that was a really interesting question. Another question by Yash: how to build interpretable models for tasks which are difficult for humans to accomplish. In general, I interpret. Yeah, I am doing one for, we're looking at DeepMind, working with DeepMind to look at AlphaZero model, which is superhuman performance chess player machine that are self-trained. And it's been really fascinating journey. We're almost ready to put out a draft. And the way that we tried is, again, advice I gave earlier, try something simple first. So what we did is we tried to align that superhuman network with concepts that chess concepts that we are already familiar with, and see, let's start somewhere, and that place should be something that's as simple as possible so that we can't overinterpret or fall into confirmation bias, and see if those concepts even exist in these networks. Because if it doesn't, then perhaps we need something completely different paradigm. What we found is, yes, some of them really exist, but there's something that happens in some time during the training that there's kind of explosion of knowledge that from which point that it was a lot harder to follow. So advice there is to just start simple and use ground truth data, ground truth synthetic data that we talked about, to make sure that your method is doing what you expect it to do first before anything. Yeah, with that, I guess I can't start. I know why I couldn't hear you. Okay. Yeah, I think I might be able to hear you now, Hyungi.
Yeah, I think, can you hear me now?
Yeah, I can hear you. Yay.
Yeah, I think due to time limitation, we have to stop at here. So thank you very much for providing an amazing tutorial for us. So thank you very much. So
Thanks for having me. This has been great.
Yes, thank you very much. So to the audience, this is the end of the lecture. So see you.